Had a brief look or consideration of the email I sent, just adding on to what I've said to you in class, that we are approaching the end of the unit, but at a sort of an unusual time. Historically, when I've taught the Year 12 spec, they haven't had Year 12 retreat, and so you've gained an extra couple of lessons there, and so it makes it more manageable squeezing it in. And I don't want to put undue pressure on you given the methods test as well. So I've said at the end of week 1 next term, we're going to finish the unit this term though, and so then I'll leave it for you guys to do some revision in the holidays and come back with some questions, okay? Please don't do nothing. All right, please do some revision. All right, today we're going to go through F1 and F2. They really link up closely together. F1's a bit longer, but I think we can cover both skills quite confidently today, which will leave us with loci to do tomorrow. All right, so what we're doing is we're solving complex equations of this form. Z to the n equals C. C can be a real number, it can be an imaginary number, or it can be a combination which makes it a complex number. And given the value of C, it's going to affect the roots that we have. So we've got a summary table here of the properties. This is copied straight from the textbook. And we'll be able to observe those once we solve the problem. So here we go. We'll start with the first one. Solve the 5 roots of minus 32i and display them on the Argand diagram. So the 5 roots means z to the power of 5 is equal to minus 32i. Now we're going to solve this using de Moivre's theorem that we learnt about last time. So what we want to do is convert this to a complex number, minus 32i to a complex number. So the magnitude of it, remember a complex number in polar form, is the modulus of z, cis, and then the argument of z. So the modulus of this is 32, it has a length of 32. And if we would consider our Argand plane, it's negative I. So that means the argument is negative pi on 2. So we have this in polar form as 32 cis of negative pi on 2. That's what z to the power of 5 is. So if we're going to solve for z, right, just think like if we had x squared is 4, the way we would solve for x is by square rooting both sides, right? If we had x to the power of 3 is 8. The way we would solve for both sides is cube rooting 8. Now what a cube root technically is, right, is it's to the power of a third. Okay? So how do we think we're going to get z by itself? We're going to raise both sides to the power of a fifth. So that's what we're technically doing here. I'm going to write it out very clearly that that's what our plan is. Cis of minus pi on 2, and that's to the power of 1 on 5. Okay, so then what we're going to have is we're going to have z is equal to 32. Let's apply de Moivre's theorem. So we're going to have the 1 on 5 here and the 1 on 5 here. Excuse me, I'm missing one thing in this line of work. Because we've performed the cube root, we need to consider the other solution. So it's plus k2 pi for k as an integer for now, and we'll define k in a moment. Okay, so, and that's to the power of 1 on 5, isn't it? So the 1 on 5 is going to apply, let's mention de Moivre's theorem again, let's recap that. If we have modulus of z cis of theta to the power of n, it's modulus of z to the power of n, cis of n theta. So that's what we're going to apply here, given the power is 1 on 5. So we're going to have 32 to the power of a fifth, cis of minus pi on 2 plus k2 pi. Okay, that's our angle. And we're multiplying our angle by 1 on 5. Okay, so we have de Moivre's theorem, the complex number to the power of n. The n applies to the modulus of z and to the angle of z. Okay, the modulus of z and the angle of Z. All right. So now let's define K, and because we have 5 roots, we're going to have K ranges from 0 to 4. There's 5, 1, 2, 3, 4, 5 possibilities there. It doesn't need to be 0 to 4, it just needs to be 5 consecutive numbers. So it would also work from K is 1 to K is 5. Because it's periodic, it's just going to keep repeating itself. But I think we start at 0, and here we have 5 roots, and so we just have, and we go from 0 to n take 1. 5 take 1 is 4. All right, now 32 to the power of the fifth. The way I think about this is 32, that's 2 to the power of 5.
Why'd you have to whisper it?
All right, now this a fifth is going to distribute, so I'm going to have minus pi on 10 plus k2 pi on 5. All right, and this follows through for k is 0, 1, 2, 3, or 4. And 2 to the power of 5 to the power of fifth, that'll just simplify to 2. Now, if we want to add these together, we need them to have the same denominator, right? So I'm going to multiply this term by 2 on top of 2. So that's going to make it k 4 pi on 10. So what we'll have is we'll have minus pi plus k 4 pi on top of 10. Okay, so I've just made them have the same denominator and brought them together. All right, so let's list our solutions then. Our solutions occur when k is 0, k is 1, k is 2, k is 3, k is 4. So we're just subbing in those values of k there. And how many solutions are we going to have? 5. Yeah. So our first solution is when k is 0. So we'll have 2 cis of, if k is 0, we're just left with minus pi on 10. All right, if k is 1, then we're going to have minus pi on 10 plus 4 pi on 10. Gives us positive 3 pi on 10. And we just keep going. 2 cis of 7 pi on 10. 2 cis of 11 pi on 10. And 2 cis of 15 pi on 10. All right, so that's all good. But I think we've got one more thing that we need to fix technically, all right? And so we just remember the argument of a complex number must be between negative pi and pi. All right, now this here is positive 3 pi on 2. All right, so probably the fastest way to convert it to the appropriate domain is just subtract 2 pi from that. All right, and same with this one. All of those are within the appropriate domain. We can see that lies between minus pi and pi, same as these two. That one's just over pi. It's 11 on 10 pi, 1.1 pi. So it's just too big. So we need to subtract 2 pi as well. Or you can just think about the eigenplane, right? Okay. 15 pi on 10, that's the same as what we can simplify that just using fractions. That's the same as 3 pi on 2. 3 pi on 2 on the unit circle is here, which means an argument for a complex number is that it's a negative pi on 2. Okay? And if you go 15 pi on 10, take away 2 pi, negative pi on 2 is what your calculator simplified. So this complex number, this one here, should be expressed as 2 cis of negative pi on 2 in order to satisfy this requirement. And the first one, same deal, 11 pi on 10. All right, so here's pi, it's just pi on 10 units further along. All right, so the correct argument for it then would be minus 9 pi on 10. All right, so our 5 complex numbers are then 1, 2, 3, 4, 5. Our 5 solutions to the equation. Okay, so it says solve the 5 roots of minus 32i and display them on the Argand diagram. All right, so I'll draw up a reasonably big one here. Now, what all of these roots, right, they're basically going to be from the centre going out, and they're going to be equally distanced apart. We'll put this one in first, minus 2, modulus of 2, cis of negative pi on 2. Okay, this can be our first complex number. All right, we also have minus 9 pi on 10, which I've said is just over pi. And then we're just spacing them out. Minus pi on 10, that's going to be here as well. 3 pi on 10, and we just have to approximate it as best as we can on the eigenplane, knowing also that they're just going to be equally spread apart, that those angles between them are going to be equal. And we need to define a scale, and a good way to do that would be to draw a circle around them and put 2 like that as a modulus of 2. To demonstrate that's the modulus, and this is their approximate location on the eigenplane. Those are the solutions to z to the 5 equals minus 32 pi. Okay, I'll just point out a couple of things here. So solving the equation z to the n equals c. So let's read it. There are exactly n nth roots of c. So we had z to the 5 equals c, and we found 5 roots. So that satisfies the first dot point. If c is a real number, the complex roots must occur in conjugate pairs. Now, we don't have a real number, we have a complex number. So not all of them are pairs, but you can see pairings here and pairings here. All right, this one doesn't have a pair. The roots will have the same modulus. All right, so they all have the same modulus of 32 to the power of 1 and 5, which is 2. On an Argand diagram, roots will all lie in a circle with a radius of 2. So we've illustrated that, radius of 2, and they're all equally spaced around the circle. Okay, so we can see that for the last dot point. Very good. Let's have a go at the second question together then. We have solve z squared equals root 3 plus I. So what is our process here? First, convert it to polar form. So you can go straight for your calculator again. The more you see these and the more familiar you are with the unit circle, the better you'll get at just going, I know that's across, the cosine value is bigger than the sine value, so this is going to be pi on, cis of pi on 6. So the angle is pi on 6. And the modulus of it is going to be root 3 squared plus 1 squared is 4, and the square root of 4 is 2. So z squared is 2 cis of pi on 6. Then to solve for z, we're going to perform to the power of half to both sides. All right, apply De Moivre's theorem. Root 2 cis, and here we're going to have pi on 12 plus k2 pi on 4. K2 pi on 2. You can treat that as plus k pi. And now we need to define k when we introduce it. The k is, first we'll say the k is an integer, and then we'll define the values of k. K is 0 and 1. 0 and 1 because we need two numbers. All right, we have z to the power of 2, so we go from 0 to 2, take away 1, is 1. Follow that through. Let's answer the question. Root 2 cis. All right, when k is 0, we'll just have pi on 12. And when k is 1, we'll have pi on 12 plus 12 pi on 12. 13 pi on 12. Alright, so if we have pi on 12 plus pi, I'm making that 12 pi on top of 12. So 12 pi plus pi is 13 pi. Now again, considering the domain, that's outside the possible domain of a numbering polar form, given that it must be between minus pi and pi, and so that'll be root 2 cis of take away 2 pi negative 11 pi on 12. All right, so our two answers then, here and here. It just says solve them. Now, like one way you can check if we're correct, right, is both of these values, what it means, whenever you solve an equation, what it means is that this satisfies this equation. This value of z will satisfy this equation. If you type this into your calculator and square it, this is what it's going to come out as. Okay? So let's have a go at 4F1 applying De Moivre's theorem here. And a bit later in the lesson we'll have a look at the question for 4F2.